Thank you very much. So it's a great pleasure to be here, and to see so many much younger people than me who are involved in the field. So today I want to be talking about the multiplicative structures on BP. So let's go back in time to around the mid-70s or so, and the following, we have a couple of E-infinity rings. We only have a couple of them. So we have Eilenberg-MacLane spectra for various rings, and we have the complex Bordism spectra and various other Bordism spectra for notions of Bordism that admit products, and we have things like K-theory. And the question comes up, does the Brown-Peterson spectrum BP admit an E-infinity structure? And this first came up in the mid-1970s because, Peter May said something about 2 years after they were originally developed was when this was put down. And so I'd like to talk a little bit about how one can show that this is actually false at the prime 2 today. But one of the reasons that this turned out to be a very difficult problem is that E-infinity rings are actually turned out to be pretty difficult to construct. Maps between them turned out to be very difficult to construct. And one of the reasons of that is that in algebra is very, very clean. It's very straightforward to build things in algebra in the way that you want because, you can just write down a ring. You can say, I want these generators, and I want to impose the relation x squared plus 1 is equal to 0. So I throw that into an ideal, and then I take a quotient, and everything kind of goes in cleanly. But in homotopy theory is a little bit messier, and you never kind of do things directly. You always act via an agent. So instead of applying the relation, what are you laughing at on this? I haven't. Instead of applying a relation like x squared plus 1 is equal to 0, what you do is you create something that imposes that relation for you. And that relation might then propagates out and does other things. So for example, if you have $20 in your pocket and you want a loaf of bread, you can go into the grocery store and get a loaf of bread. But if you give the $20 to a 10-year-old and send them into the store to get it for you, then you'll probably end up with bread and a lot of unintended consequences. And it's a very, very similar problem here. Okay, so before I get on to those kinds of things, I'd like to talk about some of the structure that we do know on E-infinity rings. So let's say R is an E-infinity ring, and H is equal to mod 2 homology. The prime in question, I may say P sometimes, but that'll be an accident, I mean 2. So H is mod 2 homology. And we look at the homology of this ring. So this has extra structure. Namely, it has Araki-Kudo-Dyer-Lashoff operations. Although those are often shortened to just Dyer-Lashoff operations. And they're usually written as Q upper S. They go from Hn of R to Hn plus S of R. And they're natural transformations in the homotopy category of R modules. And so these satisfy a number of relations. They're additive. They satisfy a Cartan formula. They have Adem relations, and they satisfy instability relations, and so on, and so on, and so on. And so merely by knowledge of these operations and knowing some calculations of them, you can start to prove results about non-existence of E-infinity structures. So one example of that is that in the proofs of the nilpotence and periodicity theorems by Devenotz, Hopkins, and Smith, there are these ring spectra constructed called Xn. So these are ring spectra from Devenotz, Hopkins, Smith. I think that I've gotten tangled. One moment. All right. From Devenotz, Hopkins, Smith. And Xn has a map down to the bottommost stage of its Postnikov tower, which is Hz. And then that has a map to Hz mod 2 or Z mod P, if you like, at odd primes. And if it had an E-infinity structure, what we could do is we could apply mod 2 homology and get this map from the homology of x of n to the homology of hz mod 2, which has another name. This is Milner's dual Steenrod algebra. And the image is known in a certain sense, but this is actually, from a certain point of view, this is small. This is a polynomial algebra on finitely many generators, whereas this is large. And the Dyer-Lashoff operations were computed by Steinberger, Mark Steinberger. And in a sense, the Dyer-Lashoff operations act in a very big way on this algebra. It's actually very, very hard to have subalgebras that sit inside here that are closed under the Dyer-Lashoff operations. So it's not possible for the homology of xn to be big enough for its image to be closed under the operations QS. So therefore, if this had an E infinity structure, then this map actually would be a map of E infinity rings, and we would get a contradiction. So therefore, we find that xn does not have an E infinity structure. And we can get a little more leverage out of this. We can say, which exact operations do we need to make this argument go, and get a little more mileage and find that we actually only need an E3 structure to get a contradiction. And so these are known to have E2 structures by their constructions as Thom spectra, like we saw in Nitu's talk, because they're Thom spectra on loops on SUM. So this kind of gives us a sharp upper bound as well. Now, if we were to try to do this for the Brown-Peterson spectrum, like so, we could play the same game. So we could map this out to its bottommost Postnikov stage, and then map that out to hz mod, oops, there we go again, to hz mod 2, and look at the effect of the map on homology. So the effect of the map on homology is that we actually get an inclusion of one subalgebra of the dual Steenrod algebra into another, namely the elements on the left-hand side that consist exactly of squares and form a subring, and that subring is the image of the homology of BP. And this map is an inclusion. Okay, so unfortunately, this is not a contradiction using primary operations. Mainly because we can also show that the homology of BP happens to coincide with the image of the map from the homology of mu to the dual Steenrod algebra that we can construct by a similar method. And this image is closed under the Dyer-Lashoff operations. So that's a little bit unfortunate. And it means that we're going to have to work harder. If we want to prove that using this kind of argument, this kind of map is an impossibility, then we need more structure on the mod 2 homology of an E infinity ring. But I just like to note, we can do a little bit of work with this, and we can find that there are some relations. For example, there's a relation that if I take C1 squared, that's an element in the homology of BP. It satisfies a relation when I apply Q8 to it. I get that this is C1 to the 4th times Q4 of C1 squared, like so. And this relation does not hold for the corresponding element in degree 2 of H2 of mu. So what that actually tells us is that if we had a map from the Brown-Peterson spectrum to mu theory, which was a map of E infinity rings, then we'd get a map from H star BP to H star mu to the dual Steenrod algebra like so. And we have a relation down here that holds and that gets mapped to a relation up here that doesn't hold. So that gives us a contradiction. So this is an elaboration on an argument due to Hu and Krish and May. Although they proved it at odd primes, and they made a kind of not such a specific argument, just something using indecomposables. So that is something, and unfortunately, I think this is kind of encouraging in a couple of ways, in that we can get some mileage, and also it took about 30 years for anybody to notice this. So there's something to be said about the fact that just kind of digging yourself in and really getting some real computations on your hand, you very rapidly can progress to something that people don't know. And I think that I really like that. OK, so we need more structure. And so the structure I want to talk about is secondary operations, which are a classical topic going back at least to atoms. And I want to discuss it in a very general framework. So what I'm going to do is I'm going to let C be a category enriched in pointed spaces. Now, when I say it that way, it's a little ambiguous what I mean by pointed spaces. And it's ambiguous because I haven't specified the monoidal structure. I mean the category enriched under pointed spaces under the smash product. So what does that mean? That for objects x and y and c, we get a space map from x to y. And sitting inside that space is a distinguished map, the base point, which we call the null map. And this null map satisfies the property that if you compose the null map with anything, you get the null map back. So that is what makes it factor through the smash product when you do composition. And composition is continuous. So then I'd like to make the following definition. So let's suppose that we have 3 objects in our category and 2 maps, F and G like so. Then a tethering of the composite, G composed with F, is a homotopy class of path from this composite to the null map in the space of maps from x to z, like so. So in particular, in the homotopy category, G composed with F has to be trivial in order for a tethering to exist. And when we've chosen a tethering, we can give it a name. And I'm going to use the following notation. I'm going to write this kind of thing to indicate that the 2 maps are kind of tied together. There's something that'll string them together and take them to 0. And if I want to give a name for that to that path, U, I'll write it up here over top. Since what's the point of writing mathematics papers if you don't get to impose asinine notation on other people? All right. So now, the next definition is when you have 2 of these in a row. That's when you get a secondary composite. So let's suppose we have 4 objects now and 3 maps, like so, and 2 tetherings. So H is tethered to G by a tethering called V, and G is tethered to F by a tethering that we call U. So we've got paths from GF to the base point and from HDG to the base point. So then, the yoga of secondary operation says that H composed with G composed with F is the null map up to homotopy for 2 reasons. So H composed with G composed with F has 2 homotopies. One of them is F composed with the homotopy V. That's a homotopy to the base point composed with F, which is F. And one of them is H composed with U inverse, since that's a homotopy from H composed with the base point. Is the base point. So now this is a loop. in pi1 of the mapping space of maps from X to W. And we'll call this a bracket, where we'll write the choices of tethering over top if we want to remember them. Okay, so unfortunately, so this is such a secondary composite is always defined if we know that G composed with F is no homotopic, and if we know that H composed with G is no homotopic. But the exact element in pi1 depends on our choices. So then, if we have the following setup where H composed with G is just homotopic to the base point, and G composed with F is homotopic to the base point, then we define the actual bracket, H comma G comma F. Now this is a subset of pi1 of the mapping space. And it consists of all the possible choices of secondary composites like this, all the possible ways that we can get a loop by choosing a tethering of H composed with G and choosing a tethering of G composed with F. Okay. All right, so just from these very general frameworks and things that we know about topological spaces, we can start to draw a lot of confusions, or not a lot of we can do that too, but we can draw a lot of conclusions about how these things behave. And so we get things that are called juggling formulas. So we get formulas that look like A bracket B, C, D is always contained inside the bracket A, B, C, D. And the bracket AB, comma C, comma D is contained inside the bracket A, comma BC, comma D. There are symmetric ones. So generally, moving something towards the middle always makes the bracket have more indeterminacy. And we also have a formula that looks like this. So we almost have this relation, except that we actually have to apply an inverse to one side. And that inverse has to do with the fact that when we were doing these composites, we had to reverse one of the paths. And so when we write down an identity like this, there's a reversal, a reflection that happens in one of the circle factors that makes this go slightly wrong. Okay, so these are called juggling formulas. And implicit in all of these formulas is that all of these composites that I've written down are actually defined, so that everything that I write down next to each other, actually the product is no homotopic. Okay, so let's talk about some examples of this kind of structure in play. So my first example is going to be when C is the category of base topological spaces, because then you have a canonical base point given by the constant map at the base point. All right, so then we can talk about a composite that looks like this. Like so. Alpha and beta. And let's call this element Y. So what do we need in order to actually define a bracket? We have an element Y in pi p of x. We have an element beta in pi m of sp. And we have an element alpha in pi n of sm, like so. And from that, we also need the relations. We need the relations that the composites beta alpha and so beta alpha has to be the null map, and we also need that Y composed with beta is the null map. And from this, we get a bracket, and the bracket is Y alpha, Y beta alpha. I'm sorry, the order of these always confuses me horribly when you do them on the left instead of on the right. So this is contained inside pi 1 of the space of maps from Sn to X, which is the same thing as the space of maps from Sn plus 1 to X if we apply pi 0. And so that's another name for pi n plus 1 of X. And so this recovers Toda's construction of what's called a Toda bracket. On the other hand, we could do something kind of Ekman-Hilton dual to this. And instead of have maps from spheres in to examine homotopy groups, we can have maps out to Eilenberg-MacLane spaces that give you cohomology. So instead, you have the following kind of example, where we have X, and we have 3 Eilenberg-MacLane spaces, like so. So what does this set up? This sets up a space X. We've got an element Y in Hn of X with coefficients in A. That's what the first map gives us. The second map, theta is a homotopy class of map between Eilenberg-MacLane spaces. That's a way that we get cohomology operations. So theta is a cohomology operation, a natural transformation from Hn of blank with coefficients in A to Hm of blank with coefficients in B. And finally, phi, the one on the right, is a natural transformation from Hm with coefficients in B to Hp with coefficients in C. And these have to satisfy a couple of relations. One is that theta of y is the 0 element in Hm of x with coefficients in B. And the second is that phi composed with theta is equal to 0. So it's a relation between cohomology operations. Like, for example, in a Dem relation, square 1 is 0, or square 3, square 2 is 0. And from this, we get a bracket, which is sometimes up to some slight pushing things under the rug. We can write this down as phi theta y. This is a secondary operation. Applied to y. And these are secondary operations in the sense of atoms, secondary cohomology operations. With a slight change in emphasis, now where is this element living? This element is living in pi 1 of the space of maps from x to k, c, p. Now this is the same thing as pi 0 of the space of maps from x to k to the loop space. And that's hp minus 1 of x with coefficients in C. So we can put these together to get secondary operations in ordinary cohomology. Or we could do these things for spectra on either side of the aisle. And as we let y vary, we get this thing, which is a secondary operation that we can plug in things. We can't plug in anything. We can only plug in things where theta vanishes. And we have indeterminacy. There's some indeterminacy according to the change in tethering because we have a subset of the mapping space and hence a subset of cohomology rather than just an element in cohomology. So indeterminacy is problematic, and it's not something that you generally deal with by diplomatic means. What you usually do is you find kind of the strongest hammer that will get rid of the indeterminacy for you, and you use that as often as possible. All right. I want to talk about, I'll just briefly mention the following example. If we instead let our category be differential graded A modules, for A, a DGA, then we can also get mapping spaces between two differential graded modules. There's usually a mapping complex, a chain complex of maps from M to N, and then we can carry that across the Dold-Kahn correspondence. And from this, we can recover the products that are written using the same notation called Mazzi products. This is Bill Mazzi, who just passed away, unfortunately, recently. All right. So for example, I'd like to talk then about one of the juggling formulas that I wrote down over there. And the juggling formula, let's say we now have a map F from another space Z to the space X. Then we could apply the juggling formula F applied to phi theta y, thought of as applied to this subset. The juggling formula, if we interpret it as composing with this map from X to Z, that says that this is contained inside here. So functions between spaces preserve secondary operations, or secondary operations are natural in as much a sense as possible. All right. So now I want to get to the situation that I'm actually interested in. In both of these examples, what we had a couple of things. One of the things that we needed was a relation. Here we had a relation between things in homotopy groups under composition. There we had a relation between cohomology operations. So now, our category C is going to be slightly different. Our category C is going to be the category of E-infinity algebras over the Eilenberg-MacLane spectrum H, which is H Z mod 2. Like so. And sitting inside here, there are certain objects that I'm going to call the free algebra on Sn. And this is defined roughly by the following property that maps from the free algebra on Sn to any E-infinity algebra A are precisely the same. So this is in the category of E-infinity algebras. This is the same as actually a map from Sn to A inside the ordinary category of E-infinity H algebras, is the same as a map from Sn to A in spectra. So homotopy classes of maps in E-infinity algebras can canonically be identified with pi n of A. So just as with spheres over here, we have certain nice representing objects so that maps out of them are homotopy elements. And same way as with these and with those, the Yoneda lemma says that if we calculate the homotopy groups of one of these free algebras, that tells us about all the natural transformations we can have on homotopy groups. So PH of homotopy classes of maps from PH of Sn to PH of Sm is equal, by the Yoneda lemma, to the natural transformations from pi m of blank to pi n of blank in E-infinity H algebras. So certain examples of these appear. So for example, we have these Dyer-Lashoff operations QS appear as elements inside there. And we can recombine these operations in various ways. Okay, great. So then our goal is the following. What we want to do is we want to show that the homology of BP, which sits canonically inside the dual Steenrod algebra, is not closed under secondary operations, secondary homotopy operations. So we need a couple of things in order to make this go. First of all, we need a secondary operation. So we have to find some relation between homotopy operations and second of all, we need to find some element in H star BP such that, first of all, the secondary operation can actually be applied to this element. And secondly, that we can calculate what the secondary operation does to this element. The operation gives something which is not in the homology of BP. All right. So for example, one of the canonical examples of relations that happen between these Dirac-Lashoff operations, QS, are the Adem relations. So as an example, if we take the Adem relations, here's an example Adem relation. So Q20, Q8 plus Q18, Q10 plus Q17, Q11, that's equal to 0. Okay, so that means that if X is any element, and by taking free algebras of not just spheres, but maybe a wedge of a couple of spheres so that we can get a few homotopy elements to combine at a time, if X is an element in the homology of BP with Q8X is 0, and Q10X is equal to 0, and Q11X is equal to 0, then we can put that together into a secondary operation. Okay. Now, unfortunately, life does not turn out to be that simple. So we could look around for quite a bit and try and figure out this kind of combination. So we have to do these two things. We have to find a relation, and we have to find an element that satisfies it, and then we have to calculate the secondary operation. So fortunately, I have one in my pocket. So let's write down this. It's very close to what the Adem relation looks like. So if X is in pi 2 of an E infinity H algebra, then this plus so this looks like a corrected version of the Adem relation. So we had an X, and it doesn't satisfy Q8X is equal to 0, and it doesn't satisfy Q10X is equal to 0, but it satisfies something approximately like that. But then when we do that, we don't have an identity anymore because Q20 gets mixed up with all this, and then so we start to write out correction terms until we get a relation. And in the interests of expedience, I just want to indicate a couple of things about this. So first of all, usually when we see secondary operations, we're used to the ones from secondary cohomology operations that just involve the Adem relations or combinations of the Adem relations. And they're very linear in nature because they come from an action of a ring, the action of the Steenrod algebra. But here we're not only involving the Adem relations, we're also using the multiplication structure. And that's in some sense forced on us because this identity that X satisfies can't be simplified down to lowest possible terms. Okay, so we find that there exists a secondary operation. Well, let's write down some of the properties of this. So first of all, it's defined on elements in pi 2 of an E infinity H algebra, or instead we could apply it to H2 of an E infinity ring, which is pi 2 of H smashed with R. Which satisfy a whole bunch of identities that are forced on us by needing to know this is 0, and that's 0, that's 0, this is 0, this is 0, and so on and so on. So the full list of relations is that Q3x and Q5x and Q7x and Q11x are all 0, and we also have those two relations there. Okay. And it takes values up to indeterminacy in pi 31 of this ring A, or H31 of the ring instead if we're using homology. And so that gives us the operation. It is also defined on, well, the thing we're interested in is the dual Steinrod algebra, so there's actually only one element in the dual Steinrod algebra in that degree, which is non-zero. So it happens that C1 squared satisfies all of these identities. The first 3 or 4 it satisfies by the Cartan formula because applying an odd operation to a square always gives us 0. And these 2 are things that 1 works out. And finally, we need to calculate what it does. What does it give? Well, the value on C1 squared, which is in the homology of BP, is C5 mod decomposable elements. All of the indeterminacy turns out to consist of decomposable elements. Which is not in the homology of BP. So that gives us a contradiction to the assumption that we had in the infinity ring in the first place. And just as before, like with the xn's, we could play a little game. We could say, how much did we actually use here? We used all these operations, and we used the relations between them, like additivity and so on, and we could figure out exactly how much n do we need our En algebra to be. So by looking at these, there's a bottom place where an operation can be applied. And so, for example, this operation turns out to be the biggest one, the one that makes the biggest leaps. And to apply Q20, Q8 to an element in degree 2, I actually need an E12 algebra. So this secondary operation makes sense for E12 algebras. And the contradiction arises for anything with the same homology as BP through degree 31. So in particular, this implies to the truncated Brown-Peterson spectrum BPN for n greater than or equal to 4. And we can fool around some more. We could like throw some completions on, or things like that. But that's where the main part of this goes. Right. So in the last couple minutes, I want to say a little bit about how we actually calculate this secondary operation. That's really where the crux of this lies, because it's really, as I demonstrated, it's really easy to start to write down relations, and sometimes you can write down secondary operations. But it's very, very easy to fail at actually getting any useful information out of that, because you might write down a secondary operation that doesn't give something interesting, or doesn't give, give 0 and doesn't give you the contradiction that you want, or maybe that you didn't want, depending on what side of this that you sat on. So how do we actually calculate the secondary operation? Well, the idea is that in looking at this list of relations, this one here pops out a little bit. I said that there was something special about that earlier in the talk. This is actually a relation that doesn't hold in the homology of mu. But actually, all of these other relations do. So since most of the relations already hold in the homology of mu, what we can do is we can express a relationship between secondary operations by juggling. So just to give some indication of how this goes, we would have some juggling formula that then pushed it over to a secondary operation related to the homology of mu. And then there would be something that simplified down, and then there would be another juggling formula that one carried out. There is a juggling formula that one carries out that does this. And by some amount of work, one reduces the question to a much smaller but actually more answerable problem. And I want to talk about what that problem turned out to be. Writing down what the juggling formulas do, it's not something that I can do on the fly, and I'm not sure that it would be terrifically productive at this exact point in time. But let me talk about where it ends up. So where it ends up is we look at this spectrum, H smashed over mu with H. So this spectrum, this is an H algebra, and it has Dirac-Leashov operations as a result. We also know its homotopy groups. The homotopy groups are actually an exterior algebra over the field with two elements, basically on suspensions of the homotopy generators of the ring pi star of mu. And then there's also a Bach-Stein, like so. So it's an exterior algebra on classes in odd degrees. So this is actually mu's version of something. This is mu's version of the dual Steenrod algebra. If you have an mu module, then an mu module x, you can take H smashed over mu with x, and that gives us something called the mu module homology of x. This thing is the dual Steenrod algebra in the sense that you get a coaction of this Hopf algebra on the mu module homology of x. And the Dirac-Leashov operations here are closely related to what the Nishida relations would be in this place. And so there are maps relating this to various other spectra. So for example, there's a map from H smash H to H smashed over mu with H. And this hits the generators in degrees 1, 3, 7, 15, and so on, but it leaves a lot of them out. So for example, the generator in degree 5 is gone. And so one can reduce the whole calculation of the secondary operations to the following question. If we take sigma x2, now this is an element in degree 5, and we apply the Dirac-Leashov operation q10 to it. Now, this is an element that's not in the image here, but its Dirac-Leashov operation could be. So does this equal the suspension of the thing that's in degree 15? So sigma x7, so this is now in degree 15. Plus decomposables. And we're very lucky that the answer is yes. And that's where after pushing down this far, the answer turned out to be yes in this instance. And so knowing information about how the Dirac-Leashov operations act here in this mu dual Steenrod algebra would not only give analogs of how we see Nishida relations in the homology of mu algebras, but then it also gives us information about this problem. All right, so I'm going to leave it there. Thank you very much. Other questions? Yeah, so how did the relation get into my pocket? Right. So I talked about, yeah, so I nattered at some people yesterday about this, but the way that it arose, first of all, I tried a lot of wrong stuff first, and that trying wrong stuff is how it becomes possible to see relations, is how it becomes possible to recognize things. But then ultimately it became kind of taking an in-depth look at Krish's old failed proof that BP had any infinity structure. And he wrote down kind of a method for doing it. And there's a problem in that paper, but the problem, figuring out where that problem actually rests led to thinking about an obstruction theory. So there's a Gers-Hopkins obstruction theory based on mod P homology for calculating moduli spaces of E infinity rings. And you can figure out what the obstruction groups are, and by doing this big Ext calculation, one finds that one finds a potential obstruction class. The first one, actually, that could possibly be non-trivial was, and it said something Koszul dual to look at the relation Q20, Q8 applied to the generator in degree 2. And then by looking at that and expanding everything out, I got very lucky. But that's where it came from, was trying to, lots of other secondary operations turn out to be excluded by the action of this Steenrod algebra and stuff like that. So it was relatively difficult to figure out something that worked otherwise without a targeted search.